let's look at a very interesting application of an exponential function. And with Newton's law of cooling, what it pertains to is measuring the temperature of some object over time. And the object might have a temperature up here, and it's placed in surroundings that have a temperature down here below it. So the object is warmer than its surroundings. Let's call this T sub S for temperature of the surroundings. And you can imagine that unless there's something maintaining the temperature of the object, the temperature of the surroundings are going to cause the object to cool over time. And theoretically, the temperature will get closer and closer to the temperature of its surroundings. So how do we model this sort of cooling behavior? Well, Newton's law of cooling says that the temperature of the object, capital T, is going to be the temperature of the surroundings, which we can see in our graph here, plus the difference between the object temperature and the surrounding temperature, T sub D, times E, this is an exponential graph, E to the K times time T. So let's discuss this model in greater detail. This is the object temperature, capital T, after time, lowercase t. So capital T and lowercase t here are the variables. Capital T and lowercase t are the variables. As time goes on, the temperature of the object changes. Okay? T sub S, we've already discussed. T sub S is the surrounding temperature. It's a constant. It does not change. T sub D is the initial, meaning at time 0, the initial temperature difference. That's what the capital D is for, difference. The initial temperature difference between the object and the surroundings, as we've shown here in the graph. And then we've got K, which is a constant. Typically, we don't know it. We typically have to find it, but K is a constant dependent on the object itself. Some objects cool faster than others and have different K values. Okay? So let's put all this together and see if we can solve a problem with Newton's law of cooling. So let's say a car engine is shut off at 205 degrees Fahrenheit on a 50 degree Fahrenheit day. And we'll assume that doesn't change. Not very practical, that wouldn't change, but this is a simple application. You might, a lot of times Newton's law of cooling can be thought of more practically in a sense where the object is in some sort of climate controlled environment where the temperature doesn't change. But this will get the point across. So it's shut off at 205 degrees Fahrenheit on a 50 degree Fahrenheit day. You can imagine that the engine is going to cool and get really close to 50 degrees over time. Okay, so the question is like, how fast does it cool and things like that. So what we can do is we can measure the temperature at some later point and see how fast it's cooling. So after 1 hour, its temp measures 135 degrees Fahrenheit. Okay, so now we can ask several questions. Question A, what will the temperature be after, let's say, 90 minutes? What will the temperature be after 90 minutes? That's a good question. after 30 more minutes, what will it be down to? And then part B, how long to cool to, I don't know, let's say 75 degrees Fahrenheit. How long would that take? Well, let's get started here on part A. For part A, we know we have the model T equals T sub S plus T sub D times e to the kt power. And so if we want to use this model, we have to plug values in for everything except for the one unknown. And so the problem with this question is, after 1 hour, that means the time is 1, and its temperature measures 135 degrees Fahrenheit. That would be capital T. We'd still need T sub S, T sub D, and K. And I can tell nowhere in this problem is the value of K provided. So the first thing I need to do if I want to use this model is find K. Use some given information to find K. So let's start with T sub S. Do we know the temperature of the surroundings? And the answer is, well, it's a 50-degree day, so T sub S is going to be 50. Do we know the temperature difference between the engine and its surroundings initially? Well, initially, the temperature of the engine is 205 and the surroundings are 50. So the difference between those will be T sub D. And in this case, T sub D will equal 205 minus 50, which is 155 degrees Fahrenheit. Then I don't know K, so I need a lowercase t and a capital T. Well, I know that after 1 hour, the temperature is 135, so those are my lowercase t and capital T. So lowercase t is 1 hour, and capital T is 135. It's important that when you pick a lowercase t and a capital T that they correspond to one another. For example, I'm not using the 90 minutes here because I don't know the temperature that goes with that time. But I do know that when my time is 1 hour, my temperature is 135. Now I have enough information here to solve for this constant K. Let's plug it all in. 135 equals T sub S 50 plus T sub D 155 times e to the K times lowercase t, which is 1. And now we need to solve for K. So we'll subtract 50 over first. And then we have 155 times e to the just K power. Divide both sides by 155. We could reduce this fraction if we want, but I'm not worried about it. Now to get rid of the e, we take the natural log of both sides. So the natural log and the e cancel on the right side. And we can see that K in this case happens to be the natural log of 85 over 155, which is approximately negative 0.6008. And it's a good sign that it's negative because the object is cooling, so it should be a negative rate or negative K value. So now this is the K we can use for our model. So now our model, with all the constants filled in and the variables lowercase t and capital T, are T equals 50 plus 155 times e to the negative 0.6008 times lowercase t. And now we know how to find a temperature after a time, or find a time given a temperature. So the question in part A, now that we have our model, is what will the temp be after 90 minutes? So now to solve that, we're asking after lowercase t equals 90 minutes, what is capital T? And so I can plug in my lowercase t, except I need to make sure that it's in the right units. All my times in the problem so far have been measured in hours, so I have to convert 90 minutes to 1.5 hours first. And now I can plug in that to get my temperature, which should be degrees Fahrenheit, because that's the unit we've used for all the temperatures. All right, so we have T equals 50 plus 155 times e to the negative 0.6008 times 1.5. And we've already solved for capital T. We just have to plug this into the calculator and get an answer. And it looks like I get approximately 113 degrees Fahrenheit. So after an hour and a half, the temperature cools to about 113 degrees Fahrenheit. All right, now part B says, how long will it take to cool to 75 degrees Fahrenheit? Well, we've already done so much of the work for part B because we have our model. So we use the same model in part B because we know our K value now. So again, we want to figure out how long, so that's a time, how much time does it take to cool to a temperature, capital T, of 75. So we know capital T is 75 degrees Fahrenheit, and we want to find the lowercase t, which will be measured in hours. So now we plug those values in. So we have 75 equals 50 plus 155 times e to the negative 0.6008 times lowercase t, which is our unknown. Now we have to solve for lowercase t in this exponential equation. So we subtract 50 over. We divide by 155 to get rid of the 155. Then we take the natural log to get rid of the e, just like we did before. And we divide, well, let's go ahead and write out this step. So now we're at the point where we're taking the natural log of e to the negative 0.6008t. The natural log and the e cancel. And so we've got the natural log of 25 over 155 equals negative 0.6008t. And last, we just have to divide by the k value, negative 0.6008, to get our time. Make sure when you type this in your calculator, you do the log divided by negative 0.6008. And I get about 3.04 for my time, and I know my time is measured in hours. So it will take about three-ish hours for the temperature to cool all the way down to 75 degrees Fahrenheit. And that is Newton's law of cooling, which is a great application of exponential functions and equations.